doesn't like to use this microphone?
We'll present standing up.
Oh, all right then.
So
It's okay.
You want me to wear mine?
Good morning. I have a great pleasure to start the Rollout 1 session. We have some small changes because John Silverstand cannot attend to our conference and sent today morning some DVX with the speech. And I propose that the first speaker will be Dave Davis, second Binczewski Arnaud, and the last presentation will be on the tape. The first speaker is Dave Davis, General Manager of Dante, and title GEANT 2, New Approach to Networks. Yes.
Well, good morning, ladies and gentlemen. I think it's quite warm in here, so I'll attempt in my talk not to add to the hot air, but to concentrate on some of the more practical aspects of the next generation of GEANT network. The title is quite consciously chosen, A New Approach to Networking, because I think if you look back over the history of research networking in Europe, it's been about bigger, faster IP networks. And I think now with the next generation of GEANT, what we're doing is looking at quite a different approach to networking, quite a different challenge in terms of networking. And some of the issues surrounding that challenge is what I would like to cover this morning. I think starting with research networking, but by definition we're talking about networks that are high bandwidth. They will be looking at utilizing the maximum connectivity available. And they will also be supporting, as well as the generality of users, they will also be supporting the particularly more complicated applications that people are developing. And the development of applications is something that goes hand in hand with the development of networks. So these two are quite complementary. And also, they are now becoming increasingly multi-protocol. I think it's interesting that the GEANT network is supporting both IPv4 and IPv6. And I'd like to make a simple correction to one of the statements that was made in the plenary yesterday about the support of IPv6. GEANT was from the very beginning designed to support IPv6 and has in fact been a dual-stack, multi-capable network for about nearly a year now. So these things are there, and they're the basic building blocks in which we are working. Two other points I think are important, that in practice the scale of technology is global. And so research networking is only really relevant in an international context and increasingly in a global context. Because if you're developing global technology, there is no point in doing it in isolated countries in Europe or indeed anywhere else in the world. The next point I think which is important is that we're talking about something which by definition is an innovative activity. It's important that it's doing new things. If research networking is just about using today's technology in a traditional way, that's not relevant. And this innovative element is, I think, what is very important in terms of looking at the future generation of research network. Now, looking at the concept of GEANT 2, one thing is quite clear, that we have the traditional IP connectivity, and this is the basis on which research networks have always been structured. And that is continuing to grow by a factor of maybe 2 to 3 a year. So this basic load of background traffic is a significant element of our planning. But interestingly enough, it is not the major traffic that one would predict in a few years' time. Looking today, then, there are applications that are being developed, applications that are being implemented, that generate significantly higher levels of traffic on a point-to-point basis than does this traditional IP connectivity. And this high bandwidth for special applications is a particularly interesting challenge looking ahead. Historically, we've had a very large number of sources and sinks of traffic and relatively small traffic flows among that very large number of sources and sinks. Now we're looking at an environment where a relatively small number of locations can generate very large traffic flows. And this is the significant difference between research networking as it's been in the GEANT era and the research networking looking ahead, is that it has to support a very much more specific requirement from customers. And really it has to provide a degree of empowerment to customers where they're using large traffic flows. Where you have a very large number of small flows, you can afford to treat those as an aggregate. But where you have very large individual flows, this means you need to look at network design separately. It means you need to look at the way you structure your network separately. And these are the main challenges going ahead as far as GEANT 2 is concerned. To respond to the expectations of the research networking community, not just in terms of the aggregate numbers of researchers, but in terms of those specific sets of researchers who have requirements for very large bandwidth between a limited number of locations. The first time we really sort of came across this in Europe was when we looked at the radio astronomy activity. And this looks to be a relatively simple application. There are a number of radio telescopes across Europe. I think there are around about 16 of them, and they each transfer data from the telescope to a central computer where the different data streams are correlated to produce images. And today, these flows are around about 250 megabits a second. Historically, it's been done using magnetic tapes and a courier. So basically what would happen is the data would be recorded at the telescope for around about 80 days onto magnetic tapes, and these magnetic tapes were shipped by courier to the central location where they were brought together to create the data images. So the round-trip time was around about 80 days. If the recording failed, you only found out about it 80 days later. And it's a very obvious thing to look at to provide over a network. So one of the things we've done in the context of GEANT is to pilot the connection of radio telescopes using networked as opposed to tape-based solutions. And in fact, if you look at the way it's implemented, then it is quite a lot more complicated than you might expect. And you can see the routes from the different radio telescopes into this central correlator in the Netherlands. And what is interesting is that you are looking at flows, individual flows on these routes of around about 500 plus megabits a second. And as a practical example, if you take the aggregate traffic that would normally flow between the researchers in the UK and researchers in the Netherlands, that aggregate traffic flow is probably around about 200 to 300 megabits of all the connectivity between the UK and the Netherlands. Suddenly you have an application that generates 500 megabits on a point-to-point basis, and you think you've got a denial of service attack. So one of the things that you start off dealing with is how do you manage these flows, because typically the only people that generate large flows on these networks today are people that are interested in bringing down the network using denial of service. So one of the interesting challenges is you have suddenly a requirement for an application that generates large flows. You have to distinguish those large flows which are legitimate from the large flows that are malicious, and that's one of the interesting challenges that we discovered when we started building this application. The second point is that it concentrates a lot of traffic in one location, and so in practice, in this particular example, when you take it to its logical conclusion, you're talking about a total access capacity in the Netherlands of around about 16 gigabits, merely to support this particular single science application. And you can see straight away that the dimension of these new science applications is very significant indeed when you compare it with the typical dimension of the aggregate data flows that exist in terms of generally supporting research network users. The other points which I think are interesting is that these flows are quite predictable, and they are around about a gigabit, probably when the experiment is running fully. And what is the point of using routers, expensive routers, to support this sort of flow, which is really very, very predictable indeed? The only thing that the router is actually doing here is providing some degree of resilience in case one of these links breaks. Using per-packet processing techniques on dedicated flows is not a very efficient way of supporting them. So you can see that if you look at the demand for this type of advanced scientific application, you can think that we need to do things differently in order to support it in the future. And this is indeed a virtuous circle, because having discovered that they could get their data into the telescope really quite efficiently, the radio astronomers also realized that they could get the data from the data center there out to individual researchers as well. And so what you've got is a double success here. By providing the support for the radio astronomy activity in the first place, you've enabled them to do better science. They can use more bandwidth, they can look further back in time, they can do it in real time, they can observe incidents as they happen as opposed to observing incidents 80 days after they've happened. And also there is another benefit, that the data which is available, the correlated data here, is now available back to the individual scientists as well. And you can see that by providing more direct support for this type of application, not merely have you improved the application, but you've given other opportunities in terms of science as well. So this has been a very virtuous circle in terms of supporting radio astronomy. But it does show a number of things. It shows that you're dealing with very high-speed flows by conventional standards, and you're dealing with them on a much more point-to-point basis than has historically been the case in terms of the traffic flows that you see on the pan-European network. Now, one of the things that is interesting is if you look at the way the costs of the basic building blocks of communications rise, what I'm plotting here is the relative cost of DWDM equipment capacity and the relative cost of routing equipment, particularly interfaces, as you increase in speed from to the 10 gigabit mark. And you can see that whereas with transmission equipment you get economies of scale, 4 times the capacity of a DWDM system is not 4 times the cost. This is not currently the case as far as routers are concerned. As you increase the speed of routers, the cost goes up linearly. And this is quite a frightening prospect, because what it's showing you is that if you were back here in the good old days, the cost of routers was not really a significant point. Now the cost of routers, and in particular the cost of very high-speed interfaces to routers, is a very, very significant element indeed. And unless these lines alter their shape, it shows you that as you go faster, the cost that will dominate as far as you're concerned is the router interface cost and not the transmission cost. And so one of the practical things that you have to face if you're looking ahead is how can I build faster networks and yet not be crippled by the bills that I have to pay to Juniper or Cisco. And that's a very interesting challenge in terms of looking at the future design of a pan-European network. Because now the numbers that start to dominate are not the transmission numbers. The numbers that start to dominate are actually the interfacing costs in terms of routers. And if I look at the latest sort of costs that we're seeing in terms of the tender activity that we're running for GEANT 2, then the cost of interfacing a 10 gigabit wavelength is probably about 2 or 3 times now the cost of actually acquiring that wavelength in the first place. And if you recognize that one of the major requirements that we're trying to address is point-to-point flows, then you have to ask yourself the question, do we really need to use expensive router interfaces to deal with traffic that is essentially quite predictable in terms of where it wishes to go? There is another reason why you would look again at the cost of hardware. And what I'm doing here is comparing the interfacing costs of switches, which is the white, and routers, which is the red. And this is a blended price of a router interface. It's from a company called Hochstapler Routers based in Germany. And you can see that it's a very dramatic difference between the cost of interfacing routers and the cost of interfacing switches. And really, the logic of this is quite simple. If you are dealing with a network where you have large and predictable flows, why incur this sort of cost when actually all you may need to do is incur this sort of cost? Now, nobody is denying the continuing requirement for a pure IP service. That's certainly true. But if you look at the traffic predictions, then you will see that the IP service will grow, and it will continue to grow. But today, the sort of typical traffic flows that we see are a few hundred megabits of aggregate traffic, whereas looking at the scientific applications, we can see applications that are capable of generating a gigabit worth of traffic on a point-to-point basis today. And that is the requirement which we have to address in order to meet the future needs of the research networking community in Europe. And that is one of the major objections of the GEANT 2 activity and why it is a new direction in terms of networking. So the traditional concept would be that we're now in a position to probably on quite a lot of European routes afford multiple 10 gigabit wavelengths. And the question is, do we use a router-based solution with all the issues in terms of interfacing costs, or do we look at some other sort of approach? And in practice, what we've got here is a typical sort of setup. You will see gigabit Ethernet, the so-called light switching initiative, this nice gigabit Ethernet here, as being one of the major building blocks looking ahead, is the requirement to use gigabit Ethernet streams across this network, as well as the generalized traditional traffic. And in practice, this is not the concept we're likely to pursue in any real sense of the word. And we're not likely to pursue it, A, because it's an unchallenging concept, and B, because it's a very costly concept. So much more likely, and this is the sort of approach which we're currently investigating in some considerable detail, is to use this hybrid network where we will use a mixture of switches and routers. And in fact, we probably need fewer routers using this than we currently have today. This has the very significant advantage that you can actually deal with the point-to-point flows because you can switch them, and you could switch them probably initially using gigabit Ethernet as a presentation method, subsequently genuine light switching, so we might have some real light switching experiments on the basis of wavelengths. And the routers are still there because they're needed for the base load of traffic, but the very significant high bit rate requirements are met much more by the switches than by the routers. And at the moment, this is the architecture which we're investigating. This is the architecture which we're expecting to procure for the next generation of GEANT. So not a simple IP architecture, but a much more complicated hybrid architecture, which raises all manner of interesting issues about how you control these switches, how you control these flows, issues that you don't really see in the context of IP. So that's one of the major challenges, is you can build this, you can put it all together, but how do you make it work? What this means in terms of the point of presence design is you will have probably a mixture of dark fiber and acquired wavelengths, essentially via switches into the routers, and the existing routers would be sufficient for the future traffic of the GEANT network looking ahead, purely at an IP level. So most of the interest is in terms of acquiring and operating these DWDM-based switches. And that will be a new area of technology. It's an area of technology which appears to be significantly cheaper, but the control issues, to be frank, are things that have not yet been resolved today. And most of the challenges will be around making these switches work. Initially, you will use a network operations center. It's a relatively easy way of configuring them. But in practice, what you want is a much more dynamic approach to making these wavelength paths work. And I think that's one of the big technical challenges which is built into the research program of GEANT2, is to make all of this technology, which is interesting in its own right, work for the users. And one of the things that you have to look at is providing user control, and the other thing you have to do is to make sure that that user control is protected so that only the right sort of users can actually exploit it. If you look at the technical program of GEANT2, which is something that's been running for some months now, we're investigating very clearly the issue of transmission costs, because although in certain parts of Europe wavelengths are remarkably cheap now, that is certainly not true across the whole of the geography of Europe. And in certain areas of Europe, implementing one's own transmission solution looks to be really quite cost-effective in terms of building the network infrastructure. And so that is a change compared with the traditional approach. I think there is a certain skepticism regarding 40 gigabits, and there are several reasons why this skepticism. If you look back at the Serenade study, the strategic study which Terena organized in terms of the future direction of European research networking, there was very little interest that the manufacturers expressed in terms of 40 gigabits. Now that's changed a little bit now. I think it's fair to say that you start to see 40 gigabits as being something that's appearing on the horizon. But can you afford a router interface at 40 gigabits, which would probably cost you around about €1 million a year as a basic investment, and you need two of them? That's the very difficult question, is if you've got these capacities, and actually you don't really want to use them all for IP, why would you spend that sort of money on router interfaces? So there is a degree of skepticism regarding 40 gigabits. I think it's fair to say that the initial building block that we will use is multiple 10 gigabit wavelengths, because they're cost effective and they're cheaper in practice than the interfacing cost of those wavelengths onto routers. The interfacing cost is a very practical issue. I think one of the things we will learn in the next several months is what it will cost us to build this hybrid architecture. We know clearly that it would be cheaper than building the sort of traditional IP architecture, but we are learning something about interface costs. And certainly this optical cross-connect is one of the very clear building blocks that we will attempt to use. We also think that all optical is some real way off. I mean, the idea of really being able to switch light in some serious way is interesting, but I think it's a research topic at the moment. It's not a topic, if you're implementing a network in the next 1 to 2 years, that you would bet the network on it. And of course, once you've got this much more sophisticated network where you're not just worrying about providing end-to-end connectivity for packets, you're providing some reasonable amount of end-to-end performance for users, then you have to, A, ensure that that performance is there, but also be sure that the people that are exploiting it are the people that are allowed to exploit it, because you're actually talking about users now capable of taking 10, 15, 20% of the total network capacity at one go. And so there is very much an emphasis on authorization and control issues. These are the sort of technical issues looking ahead that have never really been a factor as far as research networking is concerned on a pan-European basis. We've played with IP quality of service and we've done some interesting things in that area, but the reality of being able to offer controlled quality across multiple networks is the very big challenge that we'll be addressing in the context of GEANT 2. And of course, it's not just a pan-European challenge, it's basically a national challenge, a multiplicity of national challenges to make this work. If I look at the conclusions I draw, one of the things I think that's nice about IP is you can plug it together and it works. It's very much a lowest common denominator approach. But what we're looking at here is certainly not a lowest common denominator approach. And when I say back to the challenge of the 1930s, if you look at the development of telecommunications prior to, say, 1930, there was a series of national systems that were developed. But the interconnection of them in a global manner was something that was actually a challenge for the technologists in the 1930s. Because they had to offer some reasonable level of end-to-end guarantee, we are now in a position of having to offer users some reasonable level of end-to-end guarantee. Because if we do not make that offer, users will build their own networks. They will not be empowered by us, they will empower themselves. And I think that's the major challenge that we face. So in a sense, if I look at the people that worried about telecommunications in the 1930s, worried about providing end-to-end performance, that is the challenge that we're addressing in the year 2000 and 2010. And that's going to be very interesting to see whether we learn from some of the mistakes they make or whether we'll simply make our own mistakes. But we do have a fallback. If it all fails, we can simply go back to building bigger, faster IP networks. I hope it won't fail, but it's nice to know that if you're taking risks, you do have a backup scenario. Thank you.
Questions? Yes, please.
John Graham from UK Light. Di, one of the things you didn't really allude to in your conclusions is the fact that some of the NREN users are currently building their own circuit switch networks, such as Netherlight and UK Light. Do you anticipate these being subsumed, partially subsumed into this new version of GEANT, or how do you see the coexistence of future GEANTs with the current light networks?
Well, I look at the light activities as being primarily experimental. I mean, I think they're called light. That's a little bit of a misnomer, in fact. I think calling it gigabit Ethernet would be a rather fairer description. Less sexy and exciting, but nevertheless perhaps a more appropriate label. In practice, what you have to recognize is that GEANT is about high-quality production services right across Europe for all NRENs. And so that you can do things in a subset group, and it's very relevant to do that in an experimental environment. If you're offering something in a production environment, that has really to be ubiquitous. And I think in practice what you will find is that that sort of service becomes a fairly routine part of GEANT and the NRENs in the next 1 to 2 years. And the experimental side will move on to other and more challenging things.
On one of your technical slides you showed SDH switches, and I was astonished to see the label SDH. Don't you think that Ethernet switches would be cheaper today, and also the Ethernet interfaces on the routers are cheaper than the SDH ones?
That's correct. I mean, I think what we will be acquiring in terms of connectivity, a lot of it will be SDH presentation wavelengths. So from that practical point of view, you will have an element of SDH, at least in terms of the framing that you need in any case for synchronization purposes. I also have a view that if you look 2 to 4 years ahead, gigabit Ethernet will not be enough. And then there is a question as to what benefit you get in terms of 10 gigabit Ethernet as opposed to 10 gigabit wavelengths.
Next questions, please.
Well, we're going to set up there. Di's talk, I think, is a nice segue into what I'm going to talk about. We face many of the same challenges in Canada as we do in Europe, so you'll find I'll be talking about some of the same issues. So for those who don't know me, I'm Bill St. Arnaud with Canary, and I'll be talking about the CNF4 network that we've deployed across Canada. So this is our current network map. There's been some changes since the last network update. The most important being we've added now a third wavelength across the country, and this is just being turned up now. It should be this week or next week. What was interesting about this, we issued an RFP, was the responses for this and the costs. We're seeing now wavelengths about 6,000, 7,000 kilometers for costs less than 300,000 euro per year. So really quite a dramatic cost. The green lines on this, so CNF4 is made up of both of dark fiber and wavelengths. The green lines are all the dark fiber, largely provisioned by our regional networks, and the red lines are our various wavelength services across the country. And we also provide dark fiber in the metro areas and so forth. This new wavelength will also be an SDH as opposed to SONET, and we'll be using the new Nortel OME 6500 switches on this and interoperating with our existing Cisco ONS 15454s. The Nortel is a very similar switch, except it's an SDH switch, and so there's some interesting challenges there. Principally, you think that SONET and SDH are standards, interoperable standards, while they're not, and so there's some issues of control management and so forth. Nothing insurmountable, but there is some challenges. The biggest application for this new wavelength is we have a number of 10 gig requirements, particularly from our high energy physics, but also a couple from our astronomy people, but also for layer 1 transit services. We're working with a number of people, groups here from Europe and from Asia, and we're now offering this layer 1 transit so European networks can directly peer with their Asian counterparts or American counterparts across CNF4. And I'll talk a little bit more about that in a minute. As I mentioned, we're now at 3 10 gig wavelengths. We're probably going to have to acquire perhaps 2 more 10 gig wavelengths in the next year or so based on the demand we're seeing from our users and from the international community. And given the costs, we think it's quite affordable. In fact, we're at the point now where it's almost cheap enough for an individual university or researcher to buy their own wavelength at 300,000 euros per year. We can see within 2 or 3 years that the cost will drop down that much. Canada, we're facing a significant challenge with dark fiber. In the last month or two, we've had a significant consolidation of our carrier market. We've gone from 6 very competitive carriers, we're now down to 2. And the market's really dramatically changed. The availability now of dark fiber has changed dramatically. And our major carriers now acquired all the national fiber, and they're unlikely to sell any of that. So when I'm talking to people, whether by fiber or wavelengths, generally the economics go for wavelengths, but your long-term stability, I encourage is to go to fiber, because I think you'll see consolidation in many markets, particularly in smaller markets like Canada, where you may not have enough competitors. As I mentioned, the third wavelength primarily support both 10 gig and some international transit services. Most of the research institutions and universities in Canada are connected with metro dark fiber to a regional network, and the regional networks are operated one for each province. Canada is very much like Europe. In fact, some of our provinces probably have more power and independence than European countries, the way Canada is structured federally. And so CNF4 is sort of the equivalent to GEANT. We just provide a backbone, and in each province in Canada there's a regional high-speed network, mostly based on dark fiber. And these are some of those networks in the different provinces in Canada. We now support this end-to-end light path capability using SDH or SONA channels framed with GIG-E to most of our institutions. And we also now provide to many of them a bypass capability. We found this is the only way we can really solve the last mile problem. Most campuses have a very low, a relatively low speed border router and firewalls and so forth, and it's a major choke point for these high-end experiments. And so to get around that problem and working with the institutions, we have a small funding program where we've used now local dark fiber and CWDM to bypass the campus network altogether and to address some of these very high-end needs. And it's gone fairly well. The university security people are generally comfortable with this because it tends to be only for end-to-end applications. We're not connecting them to a general IP network, so there's less threat of backdoor security challenges and so forth. And it does get some of these high-end researchers off their back, because the cost of upgrading a campus network to support 10 gig-E generally is very, very expensive as opposed to putting in a new fiber or CWDM. We're also using the new 10 gig-E CWDM. There's a couple companies produce this product. And this is very slick, very inexpensive. You can go right from XFPs now, the XFP lasers are coming on the market, right through a passive coupler. And so for only a few $1,000s, you can light up to about 20 kilometers with 10 gig-E. And some companies now also combine 10 gig-E with also gig-E CWDM for a few $1,000s more. So it's a very inexpensive solution, allows you to connect up multiple servers, bypass the campus, and directly into our POPs or light paths. The other thing we're actively discussing, and this is a very controversial topic, as you imagine, there's no decisions, I just wanted to highlight this, is that we may get out of the general purpose IP business altogether. Just as we've got out of the commodity internet several years ago, like ourselves and Internet 2, we're talking about doing this as well on a national basis. There's several drivers for this, but primary purpose is the large volume of peer-to-peer music and now film file sharing we're seeing. There's several new products out there the kids are using. Some of this darknet stuff that does, and the new CASA that does all this encryption and port hopping, and they're now swapping DVD movies all the time. So what we're seeing is that the number of students doing this stuff is dropping, but now they're transferring DVD movies and the traffic volumes are skyrocketing. And so this is, some days this is 75 to 90% of our IP traffic. When we measure it. And then the other thing is you've got to measure it correctly. Normal measurement tools will not only show about 30% on your network. But so they're using DNS, they're using web, and they're using FTP, and they're hiding behind these protocols to transfer their data. And so we've got some products, one's called a local company called QVision, which does signature analysis, actually rips open each packet. And when we did that, we discovered the volume of peer-to-peer is significantly higher than it's measured by normal methods. So, it hasn't caused any congestion on the network, so haven't done anything yet, but there's several concerns. One is the optics, of course. When you get government funding, if your single largest application by aggregate traffic flow is peer-to-peer, it doesn't look as good. And secondly, in Canada, our government has a copyright tariff. I don't know if European countries have this, but on every CD, every memory chip you buy in Canada, there's a tax. And this is to compensate artists directly through a tariff program. And so now the government's talking about also extending this to internet networks, anybody who carries IP traffic. And given the volume that we have, we would then have to end up paying millions, if not tens of millions or hundreds of millions of dollars to this copyright board to compensate artists. And so rather than doing that, we may say we're going to get out of the general IP business or for research and encourage our regional networks to directly connect to each other and let them handle that problem and collect those tariffs if they so want. And they may back out of it as well. So it's an active discussion we're having, saying if this comes to pass, this may have an impact on our architecture. Nobody wants to start paying large amounts of money. And so we may have to aggressively move more and more end-to-end light paths and get away from the general IP business because of this tariff threat. So CNF4 may be really focused on just international peering, layer 1 services, and connecting a large number of specialized end-to-end applications, which we're seeing a significant number coming online. particularly in very large science and instrument applications like Di demonstrated in the EVLBI. One of our big areas is for what are called ocean observatories. Several sites off the east coast and west coast of Canada, they're deploying fiber optic cables on the ocean floor with TV cameras and a variety of sensors. And these sites are generating phenomenal amounts of data and need their own dedicated networks. And so things like this are probably going to be one of our major application areas for supporting government science labs and these high-end applications. So as you know, we've developed a software called user-controlled LightPath software. And this is what we're using now across CNF4, and I know a number of regional networks here in Europe and Asia are also experimenting with the technology. Well, one of the unique features of CNF4 is we partition our SDH and SONET switches, and then we give control of that partition to a specific end user. And then they can connect these partitions together on different switches and create their own networks. So they can create their own discipline-specific networks or application-specific networks. We use Globus Toolkit 3 to do this. We use grid technology not to support connected computers, but to allow this management of these switches. And this is very exciting for us, and we have developed several different versions of this, and we're now deploying this across the network. And allows us, as I say, to create these now networks, IP networks, not optical switch networks, but IP networks that are much finer grained. So our high-energy physicists now have their own IP network connecting about 6 sites across Canada, completely independent of our general purpose IP network. And we're also, some of our grid users are this, and we see a number of other applications where people have their own sort of private IP network, and which they can manage, they can configure the topology and so on and so forth. And I know HENET and I2CAT and the LECF people here are also experimenting and testing the software out as well, and other groups around the world. And what it allows you to do is to take that model of gigapops and so forth and really allow a much finer grain multi-homing of IP networks down even to the server level rather than just terminate the campus border level. Now, I'm going to talk a lot more. I'll give you another presentation tomorrow in the optical panel 2, and I'll get into a lot more technical detail on the architecture behind that. But here are some of the applications. As I say, we provide Layer 1 transit services. So Korea, Ireland, HENET, and Taiwan have acquired Layer 1 GIGI circuits across CNF4, and they can control those circuits with the UCLP software. So in effect, it's like buying a service from a carrier, but now they can manage those services, and they can peer directly with each other, or they can route these circuits to the Chicago Starlight or to the US FedNets, whatever they want. Or they can peer directly between Europe and Asia. And it's completely under the control. They don't have to come to us to get management approval or anything like that, or for us to set up the circuits. And we're in discussion with several other countries, both Europe and Asia, to extend this capability to them as well. We're also now, for many of our regional networks, are providing them with a Layer 1 restore and protection, so they can back each other up. Canada is very much a thin, long country, despite our shape of the country, and so restore and protection, true diversity, is sometimes difficult. So we're providing light paths to our regional networks so they can back each other up, their IP networks, this way, and provides them with fast restoral capability. And again, they manage this restoral paths themselves, and they can reconfigure that as well. Other applications is for our grids, for a number of our grid projects, or what we call distributed backplanes. So for example, WestGrid, which connects up about 8 supercomputer centers in Alberta and British Columbia, they have a separate 1 gig light path connecting the back doors of these computers through GigE switches. And this circuit's only for that purpose. No other user could get on this, and allows them to really have much better performance. It's not a shared network connection, and they can move sort of to this concept of distributed backplane. And they're shortly moving to also getting a 10 gig circuit between these centers. SharkNet in Ontario already has a 10 gig facility to do this. Other things are for these other grid projects are distributed single mount file systems for things like the high energy physics and so forth. And we demonstrate this in supercomputing with SGI, where you have a large distributed global file system across many very large arrays. And to have consistent caching performance across these multiple servers, you need a very consistent, non-congested, non-shared light path network. And so that's a typical application for these types of light paths. Other ones, as I mentioned, are high energy physics now have their own IP network, HEPNet, which links about 5 sites across Canada. And again, they can control the topology. They all share a link to CERN. They connect to the CERN facility in Chicago. And because there's only one 10 gig connection to CERN, they have to share this amongst them. So rather than coming to us to say, can you cross-connect this circuit or that facility or this server, they can do it amongst themselves using the UCLP software. Some other applications, of course, we are now transmitting the forward calorimeter data from CERN through facilities provide through SurfNet, and we'd like to thank SurfNet for providing this capability. So it comes from the SurfNet facilities from CERN to Amsterdam to Canada, and this allows them to capture this data on a monthly basis. And any shared IP network, they estimate, because of servers and firewalls and a host of other problems, it would take them 80 days to transfer this type of information. The other very interesting project that's just getting started is we're going to take the low-level trigger data off the HCP and bring it directly to Canada. As many of you know, the current architecture for CERN, for the Hadron Collider, is to have a big server farm and then pass out jobs to tier 0 sites around the world. This experiment is an alternate architecture, which we're experimenting with Poland and Denmark and SurfNet, and that's to bring the actual low-level trigger data to Canada and do the trigger filtering on server farms in Canada. And the appeal of this is that it really improves the science for the researchers, is that they can change the trigger sensitivity, they can easily add more computational resources, more storage resources, if they want to change this trigger sensitivity, and it gives them a lot more flexibility. So we'll be bringing this low-level trigger data to the University of Alberta, about 250 triggers per second, 5 megabytes per trigger, and reprocessing that and shipping it back to CERN, about 100 triggers per second and a few hundred K per trigger. And then we're starting at 1 gigabit but moving to 10 gigabits if the initial tests prove successful. And so this is a new approach to some of these very high-end experiments, is really to take the raw data coming off the instruments, rather than trying to process it locally, distribute it over these light paths internationally, and it really improves the value of the science and allows a lot more processing resources to be applied to it. So we've got a number of projects to follow on with this in Canada and internationally. The other big project we have is a virtual observatory project. This is part of the global virtual observatory consortium, and large data file transfers from our University of Toronto and the University of Hawaii, and also they want to get the actual, again, raw data coming off the charge-coupled devices rather than storing it locally to be streamed back to the researchers at their various workstations. And the synchrotron is another major project like this. They're going to have 20 science stations. And again, we've got one project starting this summer. One science station off the charge-coupled devices, very similar to astronomy, produces 2 to 5 gigabits continuous data flow. So very much like Di mentioned about the VLBI, we see a number of projects where the constant data flow, streaming data, running for 24/7, and the Canadian Light Source is going to have 20 workstations, each producing this amount of data. So huge amounts of data coming off one site. And so this is what we're seeing, is that the universities now are not the major sources and sinks of data. It's these instrument sites, and only a small number of them are going to really be our major sources and sinks for data, and are going to dwarf any of the general IP traffic. So it really starts us thinking, well, there's so many issues with the general IP traffic, we may drop that altogether and just focus on a much smaller community of very high-end users and getting that data to institutions and so forth through separate connections, bypassing firewalls and routers. So obviously some very controversial issues here. I won't say there's universal agreement on this approach, but just something we're seeing coming at us and other regions of the world, and it's really making us rethink fundamental architectures and strategies in terms of research and education networking. One thing I want to stress is that many people think we're an optical switch network. I like to say we're not. I personally don't believe in any of this optical switching, all optical and ASON and ASDN. I think it's just reinvention of ATM. We believe the value of optical networking is enhancing and creating these discipline-specific IP networks, increasing the rich meshing of IP networks and allowing this greater flexibility. So we are not trying to in any way move to fast optical switching like that. Providing this user control it adds a lot more flexibility and really, I think, extends the Internet 2 model of networking from universities to disciplines and to specific applications. And so this partitioning of our SDH switches allows us to do this to create many more IP networks. And so there's a new ITU draft standard, now Y1312, Y1313 as well, and there's some work in the IETF called GSMP and Megacode, which is all moving in the same direction. Partition of this underlying switch architecture to allow more IP networking, not optical switch networking. So there's a big difference, and I'll get into a lot more about this tomorrow. So just today, what we're seeing in this forward view is CNF4, like GEANT, we're very similar. We got NRANs, you got NRANs, we got ORANs, and it's a hierarchical IP networking stack, and that's how things work today. But where we see things evolving with these multiple light paths and switch management is a greater number of IP networks. So we will still have a hierarchy, perhaps, but we will encourage our regional networks, our NRANs, to directly peer with each other and let them handle the music file sharing problem. And we will just only do the international peering. And we'll also encourage universities to directly peer with each other, but more importantly, like the high energy physics and other people, to have their own IP network using DWDM, and so that they can directly set up their own networks, bypassing the router firewall and directly connecting their specific servers for their specific application and so forth. And so it really changes management issues, changes all sorts of challenges, and creates new challenges for network management. And then another way of looking at it is to take the Internet 2 model, I like to say equals Internet 3, is this concept of gigapops. And now, rather than, as you know, the original concept is a gigapop would peer with a commodity IP network, with VBNS, with Internet 2, and so forth, but really extend that to a much richer concept. So besides having general commodity networks, general research networks, you'll have application or discipline-specific networks. One for the VLBI community, one for high energy physics, and so on and so forth. Some of these networks will be routed, some will be switched, some will go directly to servers, some will go to border campus networks. And so that's how we think things will evolve. And the multi-homing will go much deeper, past the gigapop into the campus and directly to servers. Still some open questions here. Obviously BGP, which is the general protocol for doing multi-homing, is, I don't think, it's up to the task, getting down to the server level. And so there's open questions on how that will be done. So there's some very interesting research areas here. But I think this is what DWDM, this is what optical networking will enable. Not optical switched and back to ATM, but new, richer ways of doing IP networking. So this is a demonstration. We've done this already in prototype between HeNet and Tairen in Taiwan. We demonstrated this in a meeting we had with Internet 2 and with Dante, and where Ian Kenny here going through the Globals Toolkit Web Services portal, set up a light path across CNF4 so he could directly peer with Taiwan, and he did that late at night from his desktop in Ireland in a meeting we had in March. And now they can continue to control these facilities across the CNF4 network. So they can extend that connection, of course, locally to their own servers or do whatever they want with that facility. And similarly, we got an upcoming project we're working on, which we hope to demonstrate in a couple of weeks. And this is integrating MPLS tunnels with optical networks. So I2CAT in Barcelona, they've modified our UCLP software to work with the Nortel Optera 5200. And so they're working with Communications Research Center in Ottawa to do a demonstration for a commission, a group of people coming from the EU, and where Barcelona will control the setup of this network, even the light paths across CNF4 from their end. They will manage everything from their end and then set up a traffic flow or BGP peering across this once they've set up that network. So it's going to combine user-controlled software of I2CAT's network, then connect with a manually configured MPLS tunnel across the Red Iris and GEANT networks, and then cross-connect to UCLP tunnels managed by Barcelona all the way to CRC in Ottawa. So that's some of the stuff we're doing in Canada. As I say, I'll get into a lot more of the technical details tomorrow, and also talk about an interesting project we think user-controlled software will address some of the high-performance TCP issues by physically separating into multiple channels. You can solve a lot of the challenges we have currently with very high-performance TCP. So it's a completely different approach than trying to modify the AMD in TCP that we have today. And that's all I have.
Questions?
Question. Just yell out, Victor.
Question I have is, you already said it, that you will tell about it tomorrow, but you're about thinking of having multiple IP networks in parallel, and a lot of people think, or at least in the former times, that you get cookie loops, multi-homing is not nice. What are the challenges there, and do you think that we evolved from these last times, that it is now easier, that we can, that's now solve the problem, and how do we do it then?
Yeah, no, you're absolutely right. There is some open issues there with routing loops, and that's to say, I don't think BGP is up to it at this point in time. So for the most part, I think initially these networks will be private IP networks, and they won't be exposing routes to the global BGP table. We've developed I won't call it a protocol, but a process called optical BGP. And what that does is insert a static BGP route at the server at each end. So only the servers at each end see this new BGP route, and that route is not globally advertised to the rest of the world, because that will cause a host of problems, including flapping, routing loops, and so on and so forth. And so until the larger BGP issues are resolved, we think there'll be these new BGP routes will be constrained to very limited advertised domains.
So you have a solution for the problem, or?
Yeah, it's a jerry-rigged solution. We have one.
The next questions, please.
Yes.
One question concerning the management. You have mentioned on the optical switches you are using of the global security version 3 of management. Or what kind of management?
Oh, so the Globus Toolkit 3 is what we use. It's the same problem. If you have a computer, you're trying to share the CPU cycles on a computer with different users around the world, like in the grid, replace the computer with a switch. And we're saying, here we got a switch which is going to have multiple users. So we use the Globus Toolkit 3 to manage the partitions, to allow users then also to set up light paths between different switches and create their own topology and so forth. So it's a classic grid problem, except with computers we're using switches.
Yeah, but I mean, does it get better performance or service?
No, it just provides the user, what it looks like to the user is that they got their own separate little switch now. They can do everything with that little switch, which they could do with a bigger switch. I'll be getting a lot more detail about that tomorrow. Any other questions?
Yes, please.
Let me ask a bit about the policy issues. I don't know. I mean, you didn't touch how this thing scales up. I mean, if in a year's time some demand generates and I don't know, thousands of labs around the world want to set up their light paths, how do we attack the policy issues? I mean, who is getting the light path first?
Yeah, no, I haven't touched upon that. There's all sorts of challenges in terms of light path policy issues. Light paths are still a scarce resource, so there's a lot of work being done on AAA and scheduling and reservation and so forth. We haven't spent too much effort on that because it's our belief that the light path costs are dropping so dramatically that the problem may solve itself. As I say, it's almost getting to the point where a researcher can buy their own light path. And definitely Metro Dark Fiber and CWM, that is now affordable for a researcher. So we think the problem will largely disappear where it's going to be considered a scarce resource, and you have to have all complex policy and central management. In fact, there'll be plenty of light paths out there, most of them sitting idle.
Okay, because you mentioned, I remember 300,000 per year.
Yeah.
Okay, you expect this to drop to 300?
Yes.
$300.
I could see it. 300 seems a bit much.
How much?
But the new optical technology coming out, some of the OEO stuff, and this 10 gig CWDM, it's incredibly cheap. And the XFPs, it's dropping, the prices are dropping much faster than we ever expected. And now, if the carriers are providing the light paths, sometimes it'll be a while before they pass on those cost savings. If you can get your own dark fiber, it will happen much faster.
Yes, please.
About the lack of standards in your approach. So, for example, you're using the TL1 interface management interface for specific vendor. So what about the lack of standard interface for management and control? And also, don't you think that the industry should be behind so that we push some of the standards so that there is so that there is some interoperable solution?
Yeah, so you brought up two questions. One is, yeah, the TL1, if nobody's used it, it's a very archaic, old command response type language. It's like going back to the 50s in computer programming. So we've built a shell around the, well, actually, we got this company called Monfox, which provides a web services XML shell for TL1. And we only have to modify it slightly to work with different vendors. So we first developed for the Cisco box, but we've now modified for two of the Nortel boxes. It's relatively easy to change. In terms of standards, I'm a big believer in consensus and working code. And right now, I think there's too many people going to the standards bodies with their graduate student thesis or vendors trying to position themselves in the commercial marketplace and not enough emphasis on open source working code. So what we have said, rather than going to the standards bodies, let's prove that this works. Let's develop open source code, learn from that, and then the next step to go to the standards bodies if need be. But right now, the standards bodies are too dominated by commercial interests, in my opinion. But that's my opinion.
Okay, thank you, Bill. You must. Maybe we can use a microphone.
morning. My name is John Sylvester, and I'm the Vice Provost for Scholarly Technology at the University of Southern California. I'm chair of the Corporation for Educational Network Initiatives in California, and also a member of the National Lambda Rail Board of Directors. And I'm making this presentation to you today to talk a little bit about the National Lambda Rail, which is a fiber-based research infrastructure. Unfortunately, I'm having to tape this presentation in Los Angeles. I had great intentions to come in with Good morning. My name is John Sylvester, and I'm the Vice Provost for Scholarly Technology at the University of Southern California.
Could you stay on this
And I'm
presentation?
chair of
Because
the
if
Corporation
somebody
for
will have some
Educational
question
Network
that hasn't, and you
Initiatives in
can answer
California,
this.
and also a member of the
I hope.
National Lambda Rail Board of Directors. And I'm making this presentation to you today to talk a little bit about the National Lambda Rail, which is a fiber-based research infrastructure. Unfortunately, I'm having to tape this presentation in Los
I
Angeles.
apologize, we have some small technical problem. I think that's the 1 minute we will need some for sorry.
Going to talk about today again is the National Lambda Rail, which is a recent project in the United States to build out a facilities-based capability to implement a diverse set, really, of different networking capabilities. And there were really two drivers that led to the creation of NLR. The first one is the sort of ever-pressing need for more bandwidth. I'm sure we're all aware of this, that as time goes on, it just seems that we become more and more hungry for bandwidth in support of science and, in fact, all kinds of applications that constantly seem to need more and more bandwidth in order to be able to do their work. But one of the main drivers was really the science community, as we see more and more use of distributed processing, access to remote instruments, and other kinds of collaboration really spanning the globe. And also we see emergence of large data collection projects, sensor networks, things like this, that are generating huge amounts of data. We used to think in terms of megabits. This is now, we think in terms of gigabits. And pretty soon, in fact, if Well, good morning. My name is John Sylvester, and I'm a Vice Provost for Scholarly Technology at the University of Southern California. And I'm chair of the Corporation for Educational Network Initiatives in California, and also a member of the National Lambda Rail Board of Directors. And I'm making this presentation to you today to talk a little bit about the National Lambda Rail, which is a fiber-based research infrastructure. Unfortunately, I'm having to tape this presentation in Los Angeles. I had great intentions to come and be with you all in Rhodes, but unfortunately I got delayed and was unable to leave Los Angeles to be with you there today. So we thought we'd take advantage of the technology and digitize the presentation and make it available to you. We thought about trying to do it as a live video conference, but the time difference between Los Angeles and Rhodes would have meant that it was like 2 o'clock in the morning, and that didn't seem like the best idea, perhaps. Anyway, so what I'm going to talk about today, again, is the National Lambda Rail, which is a recent project in the United States to build out a facilities-based capability to implement a diverse set, really, of different networking capabilities. And there were really two drivers that led to the creation of NLR. The first one is the sort of ever-pressing need for more bandwidth. And I'm sure we're all aware of this, that as time goes on, it just seems that we become more and more hungry for bandwidth in support of science and, in fact, all kinds of applications that constantly seem to need more and more bandwidth in order to be able to do their work. But one of the main drivers was really the science community, as we see more and more use of distributed processing, access to remote instruments, and other kinds of collaboration really spanning the globe. And also we see emergence of large data collection projects, sensor networks, things like this, that are generating huge amounts of data. We used to think in terms of megabits. This is now, we think, in terms of gigabits. And pretty soon, in fact, if you talk to some of the high-energy physicists, for example, they talk about data rates of terabits or data stores of terabits, even petabits of information. So there's this constant demand for more and more bandwidth in order to be able to support high-end science today. In addition, there are many applications in which you need to have predictable quality for the interconnection capability. We cannot afford to have variability in delay because of the interactive nature of some of the experiments that may be taking advantage of the networking. So you needed predictable quality. You need to be sure that there's going to be 3 gigabits per second available to you for a period of perhaps several hours. And it's fairly hard to do that in some of the existing sort of layer 3 routed networks that we have today. I think we've made a significant amount of progress in improving quality of service in those networks, but they're still quite challenged when we talk about really high-end data rates. There's a project at my university which is associated with an engineering research center called the Integrated Media Systems Center, where their objective is to create immersive presence. And that is to say, to be able to recreate an environment, a virtual environment, that you can't really tell from the real thing. And so they're looking at the reproduction of very high quality sound, reproduction of very high quality video, and even going into things like haptics or the ability to interact with the environment using the sense of touch. And they're doing a set of experiments to try and make this immersive presence more and more real. There's a quote from Tom Holman from USC, who's in the cinemas, a professor in the cinema school here at USC, who's actually responsible for the development of THX. The TH in THX comes from his name, and that's the high-quality sound system that you may have seen in recent movies at the theater. He has a quote that says, the bit rate of reality is 40 gigabits per second. And what he's really saying there is if you want to be able to truly create a realistic immersive presence, you really need a data rate of the order of 40 gigabits per second. Now, some people might argue about that and whether it's 20 gigabits per second or 80 gigabits per second. It doesn't matter too much. From my perspective, it's somewhere between perhaps 10 gigabits per second and a terabit per second. In any case, it's more than we have in any of our backbone networks today. So we can anticipate that we're going to see continued demand for more bandwidth in support of research in the science community, and also more bandwidth even in the entertainment industry as we try to create more and more realistic environments. The other aspect which was really a driver for NLR was the ability to have a network that can be used to do experimentation. As we talk about providing higher bandwidth networks, we realize that some of the current protocols that are in use in networks today become challenged in those environments. And so there's been a tremendous amount of work in the last 5 to 10 years of experimenting with new protocols that are better able to support this high bandwidth environment, and also that's better able to support the predictable quality interconnect, and also even new protocols that look at being able to create separable subnetworks to support communities of interest. All of that requires that we need an environment where it's possible to experiment with new protocols, new devices at the new routers, for example, or maybe even new optronic devices, and perhaps even new network architectures where we might be able to want to be able to configure networks on demand to support specific communities. In order to be able to do any of those things, we really need to be able to create subnetworks that people can experiment in such a way that they won't interfere with the sort of routine production networking that we all depend on so much for our day-to-day business and research. So these were really the key drivers behind the development of the NLR. The origins for the NLR came out of California. At least that's my perspective, of course. I am a Californian, so you might claim that I have a biased perspective, but I think it's actually true that here in California, the Corporation for Educational Network Initiatives in California, which is responsible for research and education networking in California, it provides the sort of Internet 2 type networking for the research universities here in California. And it also provides traditional production or commodity Internet for the whole education community, all the way down through kindergarten through high school levels as well. A few years ago, we realized that the existing network that we had was sort of running out of steam, and we needed a way to redevelop that network. It turned about that this, when we were entering into that phase of redesigning our network, was right around the time when the telecommunications market went through, significant challenges. The telecommunications companies, carriers, had built out a very large amount of capacity that was buried in the ground or under the sea in anticipation of huge growth in market demand for telecommunications services, which hasn't yet been realized, largely to the sort of collapse of the dot-com industry. So that meant it was an opportunistic time for us to be able to look at acquiring dark fiber and using that to build out our network in California. And that's exactly what we did. So in California, we managed to acquire on a leased basis, a long-term lease, an IRU for 20 years, a significant fiber backbone, and then build our research and education network on top of that backbone. So we have 20-year IRUs on the fiber, and we entered into a partnership with Cisco and decided to deploy Cisco equipment on that network in such a way that we could create multiple channels over even a single fiber pair. We could separate, using wavelength division multiplexing, we could create multiple networks, if you like, in parallel over the same fiber footprint. And this is exactly what we've done in California. We've built out, currently we have 2 operational networks. One is what we call the Digital California Network, which supports the production commodity Internet. And we also have the High Performance Research Network, which supports the Internet 2 type of traffic in California. Both of those are operational since last year, 2003. In addition, we have the capability to deploy additional wavelengths in support of something we call CalREN-XD, or Experimental and Development Network. And so it's possible to deploy an additional wavelength or lambda statewide to support a specific project or a specific community of interest, perhaps for experimental work or some high some scientific application that had a very high bandwidth requirement. We've just started to deploy some wavelengths in the experimental development network. The first one was we have 3 wavelengths that are 10 gigabit per second wavelengths that are supported between Los Angeles and San Diego in support of the TerraGrid project that are built on the Cowrin fiber. And in addition, we're just in the process of bringing up a link from San Diego to Los Angeles to Irvine, to the University of California at Irvine, and also to the University of Southern California at ISI, and then on from there over the National Lambda Rail, which is what I'm talking about the rest of this talk, on to Chicago in support of the Optiputer project, Larry Smarr's Optiputer project, which you may be familiar with. So we're starting to see the emergence of these dedicated wavelengths in support of specific projects or specific communities. The way that the network was built out in California allows us to grow up to 40 wavelengths on the fiber footprint that's in existence today using the equipment that's currently installed. All we need to do is to equip the equipment with some additional cards to support the additional wavelengths. And if we need to go further than that, it's possible that we can obviously acquire additional fiber if necessary. So we built this out in California, and in the process of the negotiation with the fiber providers, it became apparent to us that it would be possible to build out a nationwide network, a similar kind of capability nationwide at relatively low capital cost. And so California then, or the folks from Scenic, and also from the Pacific Northwest Gigapop in Washington State, looked around as how we might partner with other institutions or to build out really a national footprint. And that was really the origins of the National Lambda Rail, grew out of that activity in California. And so we built out a model as to how we might be able to afford to build out this national footprint. Cisco Systems was also very interested in this development, because one of the things that Cisco needs is a large-scale lab in order to be able to experiment with new network protocols, new networking devices, so on and so forth. And so there was a sort of natural affinity between what we were trying to do in California and on a national scale to build out this multi-wavelength capability, which could provide for some research wavelengths to be used for network experimentation. So what got built out in the national infrastructure is very similar to what I described in California, where we have we acquired long-term leases on dark fiber and deployed Cisco equipment, which allows us to have up to 40 wavelengths using dense wavelength division multiplexing technology. And again, the intent being to be able to support high-end scientific applications or experimental use of separate wavelengths to support separate projects. Excuse me. The initial build, which is underway right now, is to build out 4 wavelengths initially, 10 gigabits per second on each link. And then, as I mentioned before, it's capable of expanding that up to 40 gigabits as the need arises. And so the current implementation is looking at implementing 4 wavelengths, each one capable of supporting 10 gigabits per second. NLR started out as just a project, but pretty soon it became apparent that it needed to be a separate entity. And so we created it as a non-profit corporation, and the goal was to cover the costs of NLR over a 5-year window. So we view this deployment of the fiber and the operation of the network as really a 5-year project, and then we see what happens after the 5 years. It's hard to predict that far into the future in this arena because the technology and demands are changing so rapidly. And in order to be able to play, the way it was structured was that an entity had to make a commitment of $5 million US over 5 years in order to be a member of the National Lambda Rail nonprofit corporation. And so typically, it's not too many universities that are sitting on $5 million that they're ready to commit to a project like this. So typically what happened was there were consortia formed, regional consortia, that were able to pull together the commitment of $1 million a year for 5 years in order to be able to participate in NLR. And one of those is the California Consortium, it's represented by the Corporation for Educational Network Initiatives in California. So you'll see in a moment that I have a list of the organizations which are participating in NLR, and you'll see there's quite a large number of them that are participating. The initial build is a relatively sparse network, or that's the objective, is to have a sparse network with four wavelengths initially lit. This is a list of the current participants in NLR. I think this is pretty much up to date. This slide may be a little bit hard for you to read, so let me just run through the names. And these are listed in the order of which they joined NLR. So the first one is CENIC, Corporation for Educational Network Initiatives in California. Second one is the Pacific Northwest Gigapop in the state of Washington. The third one is Carnegie Mellon Pittsburgh Supercomputer Center. The fourth one is Duke University, which is representing a coalition of universities in North Carolina. The fifth one is the Mid-Atlantic Terascale Partnership. Cisco Systems actually shouldn't be this far down in the list. They were obviously one of the initial supporters of NLR, and actually the largest supporter of NLR. They did not make a $5 million commitment like the other partners did. They have made a much larger commitment in terms of equipment at, very steeply discounted prices in order to make the NLR feasible. Internet 2 is a participant in NLR. They actually committed to 2 shares, if you like, $10 million a year, over 5 years. Florida Lambda Rail, which is a consortium in the state of Florida, is a participant in NLR. Georgia Tech and the region around Atlanta is a participant. The Committee on Institutional Corporations, which is sort of the center part of the United States. Oak Ridge National Labs. The Lone Star Education and Research Network, that's Texas, to those of you who don't know what the Lone Star State is. Cornell University recently stepped up to the plate with a commitment for a membership on behalf of the institutions in New York. The Louisiana Board of Regents also is a participant for the institutions in that region of the country. The University of New Mexico, Oklahoma, and the Southeastern Universities Research Association. So as we see, there's a very broad participation in this National Lambda Rail project. And if you add up all the funds there, you'll find that it's over $60 million that's been committed to this project over 5 years. Very significant contributions. This is a picture which I borrowed from Bob Aiken's paper in the Communications of the ACM earlier this year, January 2004, which really shows how this kind of experimental infrastructure can be used at multiple different levels. On the left-hand side here, what we're showing is that you have a single pair of fibers, and sort of working our way up through the hierarchy in this diagram. So at the bottom, on the left-hand side, we are saying that we have a single pair of fiber. On top of that, we build a production quality wavelength division multiplexing network. And that's what we're building in NLR. So we're supporting multiple wavelengths, and that's at a production quality. On top of that, on the left-hand side, we can build a traditional production routed IP network like Abilene, the Internet 2 network, or GEANT, or other kinds of production quality routed IP networks. And they could either be for high-end, high-performance research use, or they could be used for AUP-free other types of services. Shifting over a little bit to the right, in the middle of the slide here, we can build a production switched Ethernet capability on top of one of the wavelengths in the network. And then on top of that, we could implement experimental layer 3 networks, where you might experiment with different routing protocols, for example. Or you could build community-based production level 3 networks. So you could have multiple different layer 3 routed networks in support of specific communities that want to have really their own network to share to keep out certain other types of traffic, such as spam, file sharing, illegal file sharing, so on and so forth. Keep that kind of traffic away from their network so that they have a more predictable network that they can work in. Shifting further over to the right, again, we can build directly on top of one of the waves an experimental layer 2 network, and to do some experimentation with different types of protocols that are really operating at layer 2 in the network rather than layer 3. Okay, and there's some examples here. The ETF distributed backplane, for example, really fits into that model, and there are many other applications of sort of what we might call lambda switching and grid type applications, the glyph type projects, which might fit in that context where we build directly on top of the waves that are available in the wavelength division multiplex network. All the way over on the right, it's also possible to consider adding in additional fiber pairs if we want to do experimentation with different optronics equipment. So we might actually have experimental devices that are operating really at layer 1. And really, in order to be able to support those on the network, you really need to have dedicated fibers so that you don't interfere with the rest of the traffic. So I think this picture is a very nice representation of the kind of capabilities that we're trying to build into the infrastructure that is the NLR. And, you know, we're not really doing anything in the experimental optical devices part of the picture at this point in time, but there's certainly a possibility to do that, and some of the contracts that we've developed with the carriers allow for relatively low-cost acquisition of additional fiber if it's necessary. I think we've talked about most of the items on this slide. This is slide number 9, just as a reference. We've talked about most of the items on here. We have sort of 20-year long-term lease agreements, IRUs, with the carrier providers. Initially, we were getting most of the fiber from level 3. In the later stages, we've actually used some different providers in different parts of the country that have better footprint. And again, it's a base level is that each of the lambdas that we've lit up so far are operated at 10 gigabits per second, lit with Cisco gear. And the initial configuration of the 4 wavelengths that we've brought up, one is to provide a layer 3 10 gig network that could be used for a production, an alternate production, Internet 2 type of capability, if you like. One of the wavelengths is being dedicated for 8 1 gig layer 2 channels, and this can be used in some of the experiments related to glyph type applications, and that's the intent, will be to use it in that kind of format. One of the wavelengths is dedicated to Internet 2. In recognition of their contribution, they requested that one wavelength on the backbone would be for their use, and they plan to use that for experiments with the HOPI protocols, the hybrid optical packet infrastructure. I think the I stands for infrastructure. And then the 4th wavelength we're currently not using. We're assigning it as a hot spare since we're a little bit concerned with a sparse backbone that we may have equipment problems occasionally, and it would be really desirable to be able to immediately switch over to another wavelength if we lost some of the optronics equipment or something like that. So the current plan is to have that as a hot spare. This is a picture of the phase 1 rollout of NLR, and it sort of goes through the set of cities that you can see here. It's a single path across the United States. And this part is currently being built. Most of it's already operational, and all of it will be by the end of the summer. This actually, I'll just step through 3 or 4 slides here which show you how that build is coming along. So this is the first section, if you like, on the east coast of the United States will be operational in August 2004. Parts of that are already completed. I'm sorry, the part on the east coast is already completed. The second phase the second part of the phase 1 rollout is on the west coast, and most of that is already operational. In fact, I think all of that is now already operational. It says May here, and it's June already, and it is in fact already operational. The next phase brings up the stretch from Chicago to Denver, and that should go into operation this month. And then a segment down in support of the Florida Lambda Rail project down into Florida will become operational in July. And finally, the last segment from Denver to Seattle we expect to become operational in August. And so that will then complete the rollout of the first phase of NLR, and it should all be operational by the end of August. The second phase, which we're already embarking on, is then to build out the southern route so that we do have a redundant ring around the country. And this diagram here shows you the currently planned southern route. It actually, as I indicated before, uses a variety of different fiber providers. The initial phase 1 was primarily on level 3 fiber. Once we move into building out the southern route, you'll see that we pick up and actually take advantage of several carriers, AT&T, Quest, and Wiltel. And part of the AT&T fiber was actually donated through through SURA in support of this project. So we have in phase 2 that completes the ring around the United States so that we do have backup capabilities, and also builds a couple of important cross-connects in the middle of the country to shorten some of the paths and reduce the cost when you want to bring up additional wavelengths. So that second part is going to be built out really in the second half of the year. I think we have already all the funds committed. We have the number of members that we need in order to be able to build out that second phase, and so that'll be built out during the second half of this year. So the question now is turning, as the network gets built out, we're starting to see the demands for, or requests for, use of the wavelengths. And so the question is now, how do we really build out the NLR business plan? What are the services that NLR really provides? I mean, does it provide wavelengths that you can acquire or purchase from NLR? Does it also provide gig-E channels, 1 gig channels, 10 gig channels, so on and so forth? And what's the structure of that? Do you have to buy it on a long-term basis, or can you request a gig-E channel for a day? We haven't really worked out all the details of what the NLR business plan are, and those will, something that's being focused on very heavily this summer in order to be able to figure out a business plan. How is it that we're going to talk about providing access to the different types of services that NLR is able to offer? Clearly, this is going to require interaction with the user community, the scientists, the network researchers, so on and so forth. How do they anticipate being able to take advantage of this network? What makes sense to them? And so those conversations are going on this summer. Once we've decided what the set of services are that NLR should provide, how should they be priced? Are we going to have 2-tier pricing, one for members and one for non-members? My guess is that NLR will really only provide services to members. And if there are institutions in some region that need access to a wavelength, they'll come in through one of the member institutions. Like in California, if one of the California institutions needs access to a NLR fiber, they would come in through CENIC, which is the sort of primary member of NLR. And I suspect that's how it's going to be worked out. The third bullet here is, how do we deal with these sort of shorter term usage of resources? You say, I need 10 gigabits for a week. How are we going to manage that? And again, we're starting to talk about that, we're starting to think about it, and it's going to tie in with some of the glyph type discussions that are also going on as a way to allocate out resources for shorter periods of time, a much more dynamic type of allocation of the capacity. And then the last item I put up here is, what about international collaborations? We're starting to see, and there's several other countries that in many respects are ahead of where the US is in this regard, Canada, for example, and Holland, where they're already doing much more of, excuse me, sort of more wavelength-based services and dedicated channels in support of user communities. How is NLR going to interact with some of those other projects around the world? And we're seeing a lot of interest coming out of Asia as well in wanting to be able to connect and tie into this NLR infrastructure in order to be able to do these allocations of community-based networks, so on and so forth, in an international arena. So these are the kinds of inquiries that we're currently seeing coming into NLR, people asking about, how do I get dedicated waves, what's the pricing, how can I get gigabit Ethernet services in support of a particular project for a year or so, how can I get access, or what is the model for 10 gig Ethernet services, and also some inquiries about short-term allocation of waves and channels. The question that's often asked is, how does the National Lambda Rail project fit with Internet 2? It really comes down to it. If you look at the folks that are involved in Internet 2 and NLR, it's really the same community, the same faces, same core goals. Internet 2 is itself a founding member of the NLR with a commitment of $10 million. The big difference perhaps between Internet 2 and NLR is that Internet 2 is much more focused on the services providing connectivity to the campuses and the international community. NLR is much more focused on the facilities. NLR owns the infrastructure, and it allows multiple networks, such as the Internet 2 Abilene network, to be built on top of it. So there is a distinction there in terms of what their objectives are. The other interaction between Internet 2 and NLR is in the hybrid optical packet infrastructure project that Internet 2 is embarking on, which is going to take sort of a mixture of using the Abilene backbone and the NLR Lambda that is dedicated to Internet 2 to build out this hybrid optical packet infrastructure for experimentation. Just as a summary, I'm running out of time, a quick summary of the key features about the National Lambda Rail. It's an interesting new research and education owned U.S. national fiber infrastructure. And I think there's a critical point there. This is the only networking infrastructure that's owned by the R&E community in the United States. Very important. Allows that community to determine how it will evolve over time. Parts of it are now operational at 4 wavelengths, 10 gigabit Ethernet, 10 gigabit on each wavelength. They're not all 10 gig E channels. That's not quite correct here. Phase 1, the first phase that we saw, is going to be completed by the end of the summer. Still a challenge in how that capability gets extended out to campuses. When you look around the country, there are some parts of the country where there is good fiber connectivity out to the individual campuses. It's certainly been a priority in California. We've made sure that all of the research universities have fiber to the campus so that they will easily be able to participate directly in NLR, bringing out this high-capacity links all the way out to the campus itself. In other parts of the country, that's more of a challenge. And so what has been happened as a result of the NLR project is that many regional projects have started up which are trying to extend out this fiber infrastructure out into the regions, out into the states, out to the research institutions throughout the country. You've still got a challenge how you actually distribute it on campus itself. You can get to the campus, how do you get out to the researcher's lab? And this is going to obviously require significant additional investment by the campuses that want to participate in this type of networking. The most interesting thing to me is how the demand will grow. We're already seeing more and more interest being expressed by people wanting to be able to participate in NLR, take advantage of it, and it'll be very interesting to see how this evolves over the next 12 months, the next 2 years. So maybe I should come back to the Torino meeting next year and give you an update on what's happened. Just as a last slide here, I give you a few pointers for if you would like to get some more information on NLR. There is a website, www.nlr.net. And I give my email address. You can certainly send me any questions if you'd like some additional information. And a few acknowledgements. Some of these slides were borrowed from some of the folks listed here, Bob Aiken and Javad Burman from Cisco, Steve Corbetto from Internet 2, and also from NLR, Debbie Montano from NLR, and Tom West, who is the CEO of CNIC, but he's in migration to become the CEO of NLR in July. So thank you all for your attention. Again, I apologize that I could not be there physically with you all this time, but hopefully this has been a useful update on the National Lambda Rail project.
John cannot attend here, but Heather Boyce and other people from Internet 2 are here, and if you have any questions, please ask them. I'm starting a discussion. If no questions, thank you for your attention, and I am closing the plenary.